Okay, thank you very much for the invitation. So the title that I announced was a little bit longer, and it introduced also the logarithmic point of view, which I will not be mentioning. So that's why I read you'll hear more about like a logarithmic tropicalization, I think, tomorrow. So there's a logarithmic version of what I'm going to get to, hopefully. Okay, so I don't know how much I will be getting into the actual work that is published with Sam Molcho, Martin Ulrich, and Filippo Viviani. And there's a sequel with Jonathan Wise that it's not yet in the archive. But I think I will just get into the very beginning of it. So it's try to explain what are the objects and the things that we study. So this is about universal compactified Jacobian. So let me introduce you the universal Jacobian to start with. So we heard already about MGN. So the moduli space of curves. Is this visible? Okay. So this is the moduli space of curves with genus G and N markings. So it's a quite nice space, as we know, smooth, irreducible stack of dimension 3G minus 3 plus N. And the universal Jacobian over it is, so I'll be denoting it like this. So this parameterizes curves. So a point here, I will be using C for a curve in MGN. And let me just don't mention the markings all the time. So markings for me will not be very important because they will not really play a role in the Jacobian point of view. They will just play a role in the combinatorial structure of the curves that I will be dealing with. So that's not very important. So anyway, everything holds in this situation. So a point here is a pair, curve plus a line bundle over the curve. So this is just a forgetful functor. And the fiber over a curve is just genus G, Jacobian, of the curve. So you see that this space has dimension 4G minus 3 plus N, as we were like in Renzo talk, he alluded to this space, like 4G minus 3 plus N. And so it has the composite. So this is a huge space, but not connected because I'm not fixing the degree. But if I fix the degree, so these will be denoting, I will be denoting with the degree here upstairs, and each one of these is irreducible, smooth, and everything. So it's the connected components of JGN. All right, so these are not compact, as we know, and there's a quite nice compactification of MGN bar, which I want to tell you a little bit about, actually, because then it's not going to be possible to say nothing about its universal, about the Jacobian version above here. So this is, so the idea is trying to complete this square with something compact here that has a nice modular description, and the nice modular description will be visible because you'll be going to be able to describe a tropicalization morphism. Okay, so, all right, so let me recall you about the points in MGN bar. So these are stable curves with N markings. With N marked points. These marked points are smooth and distinct. And stable curve means that X is nodal, so it has nodal singularities. And it has finite automorphism group when you ask the automorphism to fix the markings. And from the point of view of combinatorics, you can see this because by just asking that each time you have accept a P1 as one of the components of your curve, this P1 must have at least 3 special points. So meaning that it has to intersect the rest of the curve or have markings in number at least 3. So for all E isomorphic to P1, in your curve, he has at least 3 special points. Okay, so these are the points that we are parameterizing in MGN bar. And so this is a very nice space. Again, a smooth stack of dimension 3G minus 3 plus n irreducible. Well, everything works very nice. And to get into the boundary of these, I'll just draw a picture that you might have seen several times. So it's a picture of the G equal to situation with no markings. So this is a picture about also if you start with the Riemann surface of degree of genus 2, all the possible degenerations that from the point of view of the topology, you're going to be seeing over there. Okay, so these are the maximal degenerate curves. And yeah, and then as you saw in the right hand, I draw the dual graphs. These are weighted dual graphs, which encode the topology of the curves. So here you saw, so this is the smooth curves of genus 2. This is just encoded with a vertex with weight 2. So you have one vertex to each irreducible component and an edge which encodes the nodes between the components. You see, so this has still just one component, but one of the components has, you know, like this, has been shrinked this, so you get a node to remember that there's this thing here. And here, by shrinking this thing, you got 2 different components, each one of genus 1, and so on. Okay? And with the arrows here, I indicate the possible degenerations, which we can see from the point of view of the dual graphs by looking at contractions of the graphs. So from the point of view of the dual graphs, it's more natural to start downstairs. So these are the mostly degenerate, so these are the most interesting graphs of genus 2. I'll just write what's the genus here. So the genus of the graph is just the first Betti number plus the sum of the weights. So, so these are the 2 unique genus 2 graphs with no weights. And then you see, if you start contracting the edges, you get these arrows here, which will just be the same that you had before, but in reversed order. Okay, so this is the combinatorial picture to have in mind to think about the degenerations over there. So this is, well, use a lot this picture to think about the topology of the boundary of MGN bar.
Polynomial equation, you have a non-singular equation, and somehow there's a recipe to degenerate by killing some terms, for example.
You mean like this? Yeah, I think you can do that from different perspectives, but that's not what we. Yeah. This is really so like algebraic degenerations. You see nodes, but yeah, if you look at it from a hyperbolic point of view, then these are going to be vanishing cycles, and I don't know if this is but there's different incarnations of these. Anyway, okay, so let me just tell you a little bit more about the so the topology. The topology of the boundary is encoded by a category. By the category that I will denote it like this, GGN, which is the category of the stable graphs of genus G and N lengths. Oh yeah, I forgot to say. So if you have markings, then you just in the dual graph you include some legs in the vertices where these markings are standing. Okay, so the category of stable graphs of genus G width and length. So what's this category? So the objects, as we saw, so the objects are GW, so a weighted graph of genus G. So the genus G is, as we saw, as I said, the first Petty number plus the sum of the weights. And the morphisms are given by weighted contractions. Weighted contractions of your weighted graphs. So that's in this picture here, where you, when each time you contract a loop, you add a weight to the vertex. So the total genus must be constant, and it is if you do the right contract. So if this W prime will be induced by the contraction.
Can you say that again? Every time you add the weight, you do what? Sorry.
So if you contract a loop,
Yeah.
so you remember that in the weighted graph by adding
something to the weight.
Yeah. So you saw. So this in this way you just keep the genus invariant.
You are weighting them. I see 2 at the top and then 1, and then some of the vertices have no weight.
Yeah, which means 0. Sorry. Yeah.
0.
It means 0. Yeah. So as in this situation, right? You have 2. So it's like 2 Riemann surfaces like meeting in 3 points. So it's genus 0, genus 0, and so this I think of this as an internal node. So I think of this as if I was disconnecting, and then so it's like so this thing will be included by the loop. So it's just one invisible component that has a node, internal node. So internal nodes will be encoded by loops. Okay, so this is the weights. So the weights are a function. I think I didn't wrote it from the vertices of the graph to be at least 0, and it's just a way to record what is the geometric genus of the component that you are considering with that vertex. So from the topological point of view, so this category will encode the way that so the boundary, yeah, the stratification of the boundary. See, that's what I'm going to write now, yeah. So this is what I was writing here. So it's encoded by this category, meaning that so MGN bar is really like this joint union for all types of weighted graphs in this category of loci that I will be denoting like this. This is the loci of stable curves which have this dual graph. So stable curves in MGN bar with dual graph GW. Okay, and so it's a decomposition. Of course, I've just used. So this is just more or less because I just, if you want yeah. Sorry, I didn't say something. Yeah, this category. So objects are graphs of this genus, and which must be stable. And stable, meaning that. So I will ask that any time I have a vertex of weight 0, that vertex has to have at least degree. So the sum of the degree plus lex has to be at least 3. So basically, I'm saying that these are dual graphs of stable curves. All right. So meaning that all vertices with weight 0, then the degree of the vertex plus the number of legs must be at least 3. So this is really saying, okay, look, I'm just looking at the graphs of genus G which are dual to stable curves. All right? Okay, so this is a composition, but I'm saying something more. I'm saying that the topology of the boundary is encoded by the category. So this means that when I sit inside one of these, so these loci are locally closed, and if I try to close it up, I find, so I can describe the closure of each strata by looking at lower dimensional strata, which are encoded by these morphisms. Okay, so this is the union over all G prime W prime mapping to GW in the category of this G prime W prime. All right. Sorry? Yes. No, it's not just a partial order. So yeah, this category induces a partial order, and it says to you, it says to you which are the generations that you have starting for, but it also has a multiplicity interpretation. So this is just not, so this is my fault. It's not, I didn't write the multiplicity. So this says like 3 arrows here. So, so these 3, so the fact that you have 3 arrows here is important. You have 3 types, 3 generations, yeah. All right. Okay. So every time you should have 3. So this should be 3. Yeah, this should be 3. These are 2. You have 2 here, and again, so this is just that you have no choice here. You have 2 here, and then here you should have 2. Yeah. Which one? Yeah, the other one. I tend to forget the zeros and the, yeah. Yeah. Yes. All right.
Is the upper right too?
No, this is my mistake. So so you have as much, so you can contract all edges. So you have to sum to that number. All right, and this it's important because it says to you, so maybe in how many ways will this sit in the boundary, right? All right, so but it's true. The poset structure is important. All right, so then let me talk about the compactified Jacobian. Yes. Mm-hmm. Well, you can think of this as like divisors of some degree, and of course you can put a negative. Then you will have no sections, but it's okay. And these are all isomorphic, of course, but just multiply by a point or something like that. All right, so the compactification that I've been dealing with is let me start it by denoting it like this. So what's this? So we could think, okay, we could take all of these curves plus line bundles over this, but it doesn't work because it's easy to see that when you have points degenerating to nodes, then you'll have it's not locally free anymore. So you have to enlarge your category. So by saying so, you can, there's usually 2 choices that you can do here. Either you allow your line bundles here to become like torsion free and allow torsion in singularities, or you can modify your curves. And for me, it's more comfortable to work with this because I want to then talk about tropicalization. Okay, so what I'm going to do here is, this should be C. And then I will take X here with a line bundle. So I'm modifying the curve. So this is going to be a bubbling of this C. So I'm allowing in some of the nodes to include exceptional components. And then if I stabilize this, I'll get the original curve. and then line bundles over here. So this is a parameterizing X is quasi-stable. So meaning that X is obtained from C by inserting exceptional P1s at some of the edges, at some of the nodes, sorry. You see, I'm always thinking about the dual graphs. And so from the point of view of the dual graphs, this means that some of the edges will be divided. You insert a vertex in the middle of some of the edges, one only vertex. And then the only request I do from now on L is that the degree of L, so this is going to be a multi-degree now. You see, because you have now several components, so you have the degree restricted to each component. And I'm just asking that degree of L over these exceptional components. These are called exceptional and denoted like E. Then the degree of E in this exceptional component must be 1. All right? And so this is the space I'm dealing with. So this is a very huge space, really, really big, but it has enough limits. So so limits exist here. So we say this by saying that this is a Artin stack satisfying the existence part of the local criterion for properness, but it's highly non-separated. So you can, like your curves, the comma line bundle can have really infinitely many limits here. So what we do is that we restrict the multi-degrees of L by imposing a stability condition such that hopefully in the end you'll get unicity for the limits. So in other words, you take separated quotients of this. And so it's smooth, yeah. This is smooth. But it's it's not a finite type, of course. I'm not even so. And again, even if I fix the total degree, it's not a finite type. But it gets very nice once you impose a stability condition. So by imposing a universal stability condition, by imposing a universal stability condition, what's this? So this is an assignment of a real number to each vertex in the category of dual graphs. So it's an assignment on going from the vertices of G to R, where G varies in GGN, such that the total, so if each time that you are over a graph, the total sum is a fixed integer, such that the sum of V is an integer, equal to an integer, fixed integer for all the category. And this assignment should be universal, meaning so it's in the category and it should respect the morphisms in the category. So each time you do contractions, then the assignment should be compatible with contractions and with isomorphisms. Okay, so then this gives you a universal stability condition, and you can ask, then you write a stability, like you write a definition of what a line bundle, what does it mean for a line bundle to be stable with respect to phi, and then if you do this, let me just don't get into that because I'm just getting to the end of the talk. Then you get a separated quotient of this. So then you consider J bar Gn phi inside J bar Gn. So where so J bar, G, and phi will parameterize, so line bundle parameterizes line bundles which are phi semi-stable. And the meaning of this is that the multi-degree of the line bundle in the components of your curves, it must be like close to phi, to the assignment. Okay, so if you do the assignment like the 0, 0, 0, 0, 0, you get the line bundles that are allowed in this space, in this moduli space, must have multi-degree that is close to 0. It's not possible to take just one multi-degree, it would not be enough. But yeah, by assigning this thing, you get a substack, which in the case that you're able to do this assignment to be general, then you get like really a proper substack with a projective moduli space. So if phi is general, and this means that in the stability condition, you never get equality. Then J, G, and bar is proper and admits a projective moduli space. And it has the dimension 4G minus 3 plus n and everything. Okay, so anyway, by considering this big space over here, you can also think that you could do games like, okay, let's consider as phi varies, how does these these are different. If you assign different stability conditions, you get different quotients, and you can try to understand how do these vary as phi varies and many different things. Yeah, sorry, yeah. I'm just, yeah. Well, I'm just taking the subspace, actually, yes. It's proper, yeah. It's proper if your phi is general, yeah, yes. Yeah. Yeah, I can write it. Right. Yes, it's the balancing condition with respect to phi. Yeah. Well, yeah, you're right. This is like the degree of L restricted to I, where I is any subcurve of X, should be minus phi of Y, and this is just the sum of phi of the vertices of Ci, where Ci is any component of Y. This should be not in like the absolute value less or equal than the number of points where Y intersects the rest of the curve divided by 2. So it's very explicit, it's not hard, it's just, yeah. So if you take like Y to be the whole curve, this could be equal, then you're just saying that the total degree is this integer that you're fixing here, and yeah. And if you are in an exceptional component, then you see the 1 over there, because exceptional component meets the rest of the curve in 2 points. So it's 2 divided by 2, so the degree has to be 1. Yeah. Okay. Yes. Yeah. Compatible with like contractions and isomorphisms in the category. Yeah, of course, what you can do then to write them explicitly is that if you are in MGN bar, you have universal curve, and you can have like vector bundles and universal curve, and use those vector bundles to like construct phi's, which come from ranks and degrees in these vector bundles. And these are like called canonical polarizations. But you can do, and actually you see this induces a chamber decomposition in the space of all polarizations. And it's known that in the interior of each chamber, there's one that is attained like this, like coming from a vector bundle in universal curve. Okay, so this is JGN bar. And yeah, again, we have a picture like this. So this is toroidal. So not only it's proper, but the compactification is toroidal, meaning that you have the boundary local is like a torus like a toric variety in the boundary locally, and then you have a stratification for the boundary as the one that we have in MGN bar. So there's a toroidal stratification. And yeah, you can choose to impose the stability condition or no, or not. It's going, you have one in both situations. And what's this? So given XL, you go to the combinatorial type of your XL. So it's again the dual graph of X, and you retain the information of the multidegree of your L. So the multidegree of your L is going to be assigning to each vertex of your curve a number, which is the degree of the line bundle in that. And you know that, so this is a divisor. If you ever saw the tropical curves and divisors on tropical curves, you can see right away that this is the information of a divisor in a graph, like to start with, in G. X. So it's an assignment of, so it's a sum over the vertices of coefficients, integer coefficients on that vertex. Okay, so then you have the topological type of your point in the compactification, and there's a category that encodes the topology of the compactification, as in the previous case. So there's a category that we denote like this, QDIV GN, encoding the topology of the boundary. And it works either you decide to insert the stability condition or not. And again, so this is a category where objects are graphs and these divisors on the graph, so formal sums of integers in the vertices, and where morphisms are as before, but when you have a morphism, so you say that you have a morphism in your category if you have a morphism of the graphs pi, and this induces a natural map of divisors which will land into this divisor. So it's like compatibility with these assignments in the vertices. All right, so this category encodes the topology of the boundary in the same way as before, meaning that you have a stratification of the boundary, and so the closure of each strata is encoded by these morphisms. Okay, so this is again as before, and because of this, we can do a tropicalization map. And so yeah, this will show the picture. Well, yeah, maybe it's okay. So there's a tropicalization map. Which I will write like this. So we have this JGN bar. And so to make this precise, I should go into non-archimedian, the non-archimedian category. So I should do the analytification of this space, or that I will denote like this. So this is a space, and I take the topological space underlying this. So the points on this space are maps from spec R into your JGN bar. So where R is evaluation ring of rank 1. So you should see the points here in this topological space as like the generations of in your space over this spec R. And the tropicalization map is just looking at the central fiber of this. And so you look at the central fiber of this, and you go to, you take, of the central fiber, you take the dual graph of the so-called this C going to spec R. You take the dual, so you take the topology, yeah, this comes as well with the line bundle, sorry. So you take the combinatorial type of this family in this restricted to the central fiber. Okay, and because you're looking at something, because you're looking at spec R, which is a ring with valuation, you have a way to assign lengths to the vertices. And so you assign lengths to the vertices of this dual graph. And these lengths, so this will then maybe remember you that this is going to be a graph together with lengths on the edges, sorry, of the dual graph. So this is a data of the tropical curve, so a metric graph, and plus divisors in the tropical curve. So what I'm saying to you, like in a very imprecise way, because I don't have time, is that there's a way, so we have a nice picture for the boundary of this compactification, and using this non-archimedian incarnation of our space, there's a way to construct a tropicalization map. This is intrinsic from the fact that you're taking the analytification, so there's a skeleton out of this. But it's a topological retraction. So this is a generalized cone complex, and what I'm trying to say here is that this generalized cone complex is the moduli space of a tropical version of this initial space. So you show that, we show then, so this is our theorem A, is that this is isomorphic to what we call JGN trop. Okay, so again, we take this analytification, and then there's a way to write intrinsically a tropicalization map mapping to a skeleton of this. This is a complex of cones, of real cones. And this complex of cones, then because this map is modular, we can show that this is really landing in a space that existed already. It's a space parameterizing tropical curves, meaning graphs together with lengths in the edges, plus divisors in the curve. Okay, so. Yeah.
I mean, you already introduced that space.
Yeah,
right?
this is, yeah.
Yeah,
There I didn't have lengths, and the interpretation I'm doing from the fact that, you know, like I did introduce these bubblings in the graphs, then this will be visible here in the fact that you have like the divisors also in the edges of your graphs, which are metric spaces now, which you see as metric spaces now. All right, so
does it depend on phi? Sorry, last question.
This does not depend on phi, but it's compatible with phi. Okay, so this works for the real big space. So this is why I'm taking this thing here, because this is not proper. And then this exists, so the theorem is true in this situation, but I can include the phi, and this will behave nicely for the the phi as well. And also, when I introduce the phi, then I have something more. Because you see, like, so as I said, the tropical curve is a metric graph. You can see it as a metric graph, and the divisor on the tropical curve is just a formal sum in the points of your metric graph. And there's, so given gamma, a tropical curve, so this is a graph with a metric, and the divisor is just a formal sum in your graph. And there's a notion of principal divisor, and you can define the tropical Jacobian to be divisors modeled by linear equivalence given by being div of some rational function in your graph. So this is a torus of real dimension G. Okay, this is a torus of real dimension G. And by assigning this phi, what you do is that you are doing a subdivision of your torus, and which I tried to exemplify in this picture here. So take this curve here, so the genus 2 curve. So the Jacobian of this curve will be R2 modeled by Z2. So this is the toric picture. Okay, so this is the toric picture of this, of the Jacobian of this, is a dimension 2, real dimension 2. And the stability condition associated to this assignment in the vertices 1 and 1 will subdivide your torus in regions according to the possible multi-degrees that you can have. Okay, so this is a subdivision. And so this is a picture for this specific situation. And you can play, well, you know, like this. This is just over one curve, and then you have the global picture over the whole MGN part. It's very nice. You can do lots of computations, and there's lots of computations that you cannot do sometimes. But again, yeah, and this is, so the fact that this is a subdivision then is important also when we then do a logarithmic version of this tropicalization. Okay, so this is all I wanted to say. Sorry.
Thank you very much.